Fundamental analog circuit analysis, applying Kirchhoff's laws to continuous signals. Welcome back to our Analog Electronics series. In this video, we'll discuss how the fundamental circuit analysis laws, Kirchhoff's voltage law, KVL, and Kirchhoff's current law, KCL, apply to circuits dealing with continuously varying analog signals. As we learned earlier, Kirchhoff's voltage law, KVL, states that the algebraic sum of all voltages around any closed loop in a circuit must equal 1, 0. This principle holds true instantaneously for analog voltages. At any given moment, the sum of the voltage rises must equal the sum of the voltage drops around a loop, even if these voltages are continuously changing. Similarly, Kirchhoff's current law, KCL, states that the algebraic sum of all currents entering and leaving any node in a circuit must equal 0. This principle also applies instantaneously to analog currents. At any point in time, the total current flowing into a node must equal the total current flowing out of that node, regardless of how these currents are varying. When analyzing analog circuits with resistors, capacitors, and inductors, we often deal with time-varying voltages and currents. To apply KVL and KCL effectively, we need to consider the voltage-current relationships for each component, which, as we discussed, involve derivatives and integrals for capacitors and inductors. For circuits with sinusoidal analog signals, we often use the concept of impedance and phasors to simplify the analysis. By representing the continuously varying sinusoidal voltages and currents as phasors, complex numbers representing their magnitude and phase, we can apply algebraic techniques based on Ohm's law along with KVL and KCL in the frequency domain. This transforms differential equations in the time domain into algebraic equations in the frequency domain, making the analysis much more manageable. Understanding how to apply KVL and KCL in both the time domain, for general analog signals, and the frequency domain, using impedance and phasors for sinusoidal signals, is a cornerstone of analog circuit analysis. These laws allow us to predict the behavior of complex analog circuits and are essential for designing circuits that process continuous signals in a desired way.